All right, so now we're going to look at some molecular compounds and some of their properties. Molecular compounds are pretty much, in a lot of ways, opposite of ionic compounds. They have lower melting points, and they are mainly liquids and gases at room temperature. There are some solids, like table sugar, but those do melt at very low temperatures compared to the lovely ionic compounds. So yes, molecular compounds are mainly liquids and gases. There's my picture of liquids. There's my funny little joke. Girls pass notes, boys pass gas. Haha. All right, moving on. Molecular compounds are also pretty much predominantly only nonmetals that are in these compounds. The molecular formulas of them give us the actual numbers of atoms that are in the molecule. Hold on a sec. And to clean up that formula, so yes, the actual number of atoms in the molecule, like sucrose here, there's 12 carbons, 22 hydrogens, and 11 oxygens put together in a molecule. With our ionic compounds, our formulas showed us the ratio of ions. So we never really see an ion with a charge bigger than the number 5. So we typically don't see numbers greater than 5 in an ionic compound formula. Now with our molecular compounds, when they are molten or dissolved in water, they typically do not conduct electricity, or they will do so very little. So we call them non-electrolytes or very weak electrolytes. And again, all of this information can be helpful when we do our little lab where I give you a bunch of different compounds and you have to investigate and tell me whether they're molecular or ionic. And a big part of that is the conductivity tester, which is just fun, fun, fun. So a covalent bond, of course, is sharing of valence electrons, but a little more sophisticatedly, we say it's the force of attraction between oppositely charged nuclei and the electrons holding the atoms together. There's some repulsion between the nuclei, and there's repulsion between the electron clouds, but there's also attraction. And so there ends up being this perfect distance, this bond length, which is the distance between the nuclei at the minimum potential energy. And we see this lovely little graph. And we see potential energy over here on the left, internuclear distance in picometers. So two hydrogen atoms apart have X amount of potential energy. Well, as you move them closer together, the potential energy drops until you get to this big dip in the curve, and that's where the potential energy is the lowest. And that is the bond distance, 74 picometers. And if you try and smush them any closer together, whoosh, that potential energy shoots up because of the repulsion. And you see over here it's a balance between attraction and repulsion. Now this energy here, the dip in the potential energy, is what we call bond dissociation energy. And what that is officially is that it's the energy added to separate atoms in a molecule. So yes, that's how much energy is saved when the atoms get together. Then to break those atoms apart is the dissociation energy. The larger that amount is, indicates the stronger that the bond was holding those two atoms together. They love to interpret this potential energy diagram for covalent bonds on the AP exam, and I'm sure you will see it on our unit exam as well. So again, why is this happening? Well, here's hopefully a diagram that looks familiar to you. So we have a hydrogen atom with 1 valence electron, chlorine with 7, and they're going to share. And hydrogen is happy because it feels like it has 2 electrons like helium. Chlorine feels like argon with its 18 electrons, 8 valence. And that shared pair of electrons is a covalent bond. And so when we draw a covalent bond, it's a dashed line. We call that a bonding pair. And then the electrons that are left that aren't in the bond, if there are any, are called lone pairs. Hopefully that's just a little refresher for you. We may also see this thing called a coordinate covalent bond because sometimes a bond is formed between 2 atoms and both of the electrons come from 1 atom. This happens quite commonly here you see with our polyatomic ions ammonium and hydronium. So ammonia will add another hydrogen to it by sharing its lone pair there. And same thing, water will share one of its lone pairs from oxygen with another hydrogen to make a hydronium. So in a structure, typically an arrow pointing to the fact that where the lone pair came from and what it's being shared with is in the structure. So that indicates a coordinate covalent bond. We'll spend more time with these later. But again, ammonium and hydronium are quite often used. And here's just a little explanation showing what's going on. Like if we have ammonia and hydrochloric acid, then ammonium is there and there has a positive charge because only the hydrogen nucleus moved over to the nitrogen because the bond is with the lone pair from nitrogen. The negative charge is left on the chloride ion because the hydrogen left its electron behind. And then again, there is the coordinate covalent bond. Not heavily tested, but something good to know, especially, again, we'll use some of that information later in the year. Now, with that little diagram, I said that helium or hydrogen was happy with 2 electrons, so it could be like helium. Most other things in our molecules obey what we call this octet rule, and that's the tendency of atoms and molecules to have 8 electrons in their valence shell. Well, of course, this is chemistry, and there's always exceptions. But most often, we do obey the octet rule when we're building and drawing these molecules. Carbon, nitrogen, oxygen, and fluorine never violate the octet rule. So that'll be important information for us as we draw Lewis diagrams. There are exceptions, and even though these are exceptions, a lot of these elements also do obey the octet rule more often than not. But there's some little guys. Beryllium and boron are actually just way too tiny to really accept 8 valence electrons. And so beryllium's happy with 4, and boron is happy with 6. Then there's our big guys. Once we get to like the 3rd energy level, we start to have the D sublevels also available. And so our atoms can take on more than 8 valence electrons. So you can see here phosphorus, sulfur, chlorine, bromine, iodine, and xenon. Yes, xenon forms bonds now. They can take on more than 8 valence electrons. Again, this will be useful information as we go into drawing molecules, doing Lewis dot structures, etc. Now we can also have more than just single bonds. We can have double bonds, which is 2 shared pairs of electrons, or triple bonds, which are 3. We don't have quadruple. The most common double and triple bonds out there, the oxygen-oxygen double bond and the nitrogen-nitrogen triple bond. Now when we really think about it, all of this molecular bonding is only happening with a few elements. There's only so many nonmetals, not very many at all. And of those nonmetals, there's only a couple that are really eligible to double bond. Mainly oxygen, as we see here, sulfur, which is also in oxygen's family, and then carbon, nitrogen, and phosphorus have the ability to also form double bonds. There's even less as far as triple, because oxygen and sulfur cannot do triple bonds, at least not in the traditional sense. Carbon monoxide has a carbon-oxygen triple bond, but one of the lone pairs from oxygen forms that 3rd bond, so it's kind of like a coordinate covalent situation going on there. But as far as triple bonds are concerned, only nitrogen, phosphorus, and carbon will want to form those. So again, our number of elements eligible is extremely limited in that fashion. Again, all good, useful information as we head further into these topics. So ultimately, how do we know what kind of bond is going to form between elements? Ionic, nonpolar covalent, or polar covalent? And if you remember, this depends on electronegativity differences. When we subtract the electronegativities of the elements, it will tell us if we have an ionic, polar, or nonpolar bond. Fluorine is by far the most electronegative element. This is the Linus-Pauling scale, and it's given a 4.0. Francium, not very electronegative, 0.7. Again, this is a reflection of the tendency of where the electrons will go in a bond. More electronegative, the electrons will go to that element. And so there's some controversy about the breakoff points as far as what determines whether or not a bond is nonpolar, polar, or ionic. But you can definitely see here that the larger difference between the electronegativities, the stronger the bond. An ionic bond is way stronger than nonpolar or polar. When we have a polar bond, we have partially positive and partially negative situations showing up in the molecule. And we'll see dipoles when we talk about figuring out whether or not a molecule is polar or not. But those little squiggly things, those are lowercase delta in the Greek alphabet, so we see partial positive, partial negative. Again, a little bit of controversy. Some people say nonpolar, polar is split at 0.5, some say 0.4, some say ionic is 1.7. AP won't typically give you electronegativities and ask you to subtract and figure out bonds. They'll just kind of expect you to know that fluorines are most electronegative, so anything covalently bonded to fluorine, that's going to be a polar bond. Oxygen is next. Most things bonded to oxygen are polar as well. Chlorine, etc. There's just some bonds that we'll use over and over and over again that they're going to kind of expect you to start to know. Like the oxygen-hydrogen bond in water. That's a polar bond. And here's some other very popular polar bonds. And then there's just a few very popular nonpolar. Carbon-hydrogen, carbon-sulfur, carbon-nitrogen. Again, some people might argue they're not truly nonpolar unless there's a difference of 0. And so even just a tiny bit of difference, there'll be a slight polarity. But as far as most things we're concerned with, you can consider things with, small differences to be nonpolar. All right, I hope this helps, and I will see you soon.